Hello students, so in this video I'm going to teach one more numerical under Otto cycle. So the problem goes like this: an air standard Otto cycle is to be designed according to the following specifications. Pressure at the start of the compression process is 101 kilopascals. The pressure at the start of the compression, that means before compression, the pressure will be 101. It is obviously known that it is the initial pressure, which is nothing but P1 pressure. And temperature at the start of compression process is 300 kelvins. So again it is the initial temperature 300 kelvins. Compression ratio is given as 8. So V1 by V2 is given as 8. Maximum pressure in the cycle is 8 megapascals. So where do we come across this maximum pressure in this particular cycle? So third point will be the maximum pressure throughout the cycle. So we have to take P3 as 8 megapascals and we have to convert into kilopascals, that I'll let you know. So finally find the net work output per unit mass. So we need to find out the work output and cycle efficiency and mean effective pressure. So these three things we have to find out in this problem. Again it is not so complicated. So first and foremost you need to draw the Otto cycle, which is very well known to everybody, that how to draw this PV and TS diagrams. So 1 to 2 process will be the adiabatic compression, 2 to 3 constant volume heat addition, 3 to 4 so adiabatic expansion, and 4 to 1 constant volume heat rejection. So these are the four different processes that we know, and TS diagram also we need to draw to avoid confusion. So here in this diagram, PV and TS diagram, so QS will indicate heat supplied and QR will indicate heat rejection, and so 3 to 4 and 2 to 1 will be the work done. Okay, so this is how we need to draw the PV and TS diagram. So next one, the given data which I have already told you, P1 is equal to 101 kilopascals and T1 is equal to initial temperature 300 Kelvin, and compression ratio V1 by V2 is equal to 8. So this V1 can be written as 8 V2, and P3 maximum pressure in this problem, maximum pressure is directly given 8 megapascals. So 8 megapascals is equal to 8 into 10 cube kilopascals. So we have converted megapascals into kilopascals. So we need to find out heat supplied QS and efficiency of the Otto cycle eta and mean effective pressure, right, MEP. So first one we can easily find out, because compression ratio, whenever the compression ratio is given, so it is very easy to find out the efficiency of the Otto cycle, because the formula is very simple. Efficiency is equal to 1 minus 1 divided by R to the power of gamma minus 1, where R is R indicates compression ratio, and gamma is a constant value which is adiabatic index. Adiabatic index for air is equal to 1.4. So straight away you can find out without any confusion. So 1 minus 1 divided by a to the power of 1.4 minus 1. So finally the Otto cycle efficiency is equal to 56.47%. I hope that till here students won't get any doubt under this, because it is a direct substitution. And next slide. So here we need to find out the temperatures and pressure at every stage, like every state in the PV and TS diagram. So first T1 P1 is given in the first process, first state. So we need to find out P2 and T2, right? So the very well known formula, since it is adiabatic process, 1 to 2 process adiabatic, so T2 is equal to T1 into R to the power of gamma minus 1. So in this we can find out the T2 temperatures. So next gas equation. So to find out P2, so P1 V1 whole to the power of gamma is equal to P2 V2 whole to the power of gamma. These two formulae indicate adiabatic processes, otherwise isentropic processes. Whenever you come across this isentropic or adiabatic processes, you have to consider these two formulae. So whichever is necessary at that particular point of time, so you need to consider that particular formula. So here two formulae we used to find out T2 and P2. Okay, so P1 V1 whole to the power of gamma is equal to P2 V2 whole to the power of gamma. In this we have found out the value of the temperature after compression, that is 1856.29 kilopascals. So next thing we need to find out is V1. So we don't know, the volume is not given in the problem. So P1 V1 is equal to MRT1, and M is taken as 1 kg mass. So V1 is equal to RT1 by P1. So in this 0.852 meter cube per kg. So it is not so complicated, because we are using the simple gas equations, and compression ratio is given V1 by V2 is equal to 8. So V1 is considered as 8 V2. So V2, so to find out V2, V1 by 8, so it is 0.108 meter cube per kg. So V1, V2, P1, P2, so T2, everything is known. So then slowly, so we switch over to 2 to 3 process. 2 to 3 is a constant volume. So since it is a constant volume, V2 and V3 is cancelled in both the sides. Then P3 is equal to P2 T3 by T2. But T3 is not known. So T3 is equal to, if you substitute the values which are known, so we will find out the T3 value and P3 value, and here V3 is equal to V2, since it is a constant volume process. 2 to 3 process is a isochoric process. That is why both the volumes are same in this problem. And again we'll switch over to 3 to 4 process. So 3 to 4 process is adiabatic. Adiabatic means you have to consider this equation, T3 by T4 is equal to V4 by V3 whole to the power of gamma minus 1. Here you should understand one thing, V4 is equal to V1 and V3 is equal to V2. So to get better clarity, you need to check in the PV diagram. So you'll clearly understand why that V4 is taken as V1 and V3 is taken as V2, right? So in this equation, so you can find out T4 value, since everything is known. T3 is known, T3 is already given in the problem, right? So QS is heat supplied. QS is equal to the same process 3 to 4. Since it is constant volume process, QS is equal to CV into T3 minus T2. So QS is equal to 1637.8 kilojoules per kg. Next, heat released QR. So where do we come across this QR is between 1 to 4 process or 4 to 1 process. So 4 to 1 process is constant volume, so it is taken as CV into T4 minus T1. So QR is equal to 712.9 kilojoules per kg. So with this we have found out what is heat supplied, what is heat rejected. If we know these two heat addition and heat rejection values, it is easy to find out the the remaining thing. So work done. So work done is equal to heat supplied minus heat rejected. So heat supplied, the value already we have found out, minus heat rejected also the value we have found out. So with this we'll find out the work done value. So next thing is mean effective pressures. Mean effective pressure is equal to work done divided by V1 minus V2. Work done already we have found out, V1 V2 both the values we know separately. So we'll put the same values and find out the mean effective pressures. So these are the things we have found out in this formula. So very simple one. First we found out the efficiency of Otto cycle. Then we have taken the process 1 to 2, and you should know so what kind of process it is and what are the formulae we have to use. If you know these two things, it is very easy to understand. So T2 is equal to T1 into R to the power of gamma minus 1, or P1 V1 whole to the power of gamma is equal to P2 V2 whole to the power of gamma. So we have found out all the values, and then 2 to 3 process constant volume. So we have removed the volume terms and we have found out the remaining things. And 3 to 4 is again adiabatic process. So adiabatic process formula we have written, and then heat supplied, heat rejected formula we have written and found out the values. And then we have found out the work done formula. Work done is QS minus QR. So we, in that way we will find out the work done, and then mean effective pressure is equal to work done divided by V1 minus V2. So with that we will find out the mean effective pressure values. So this is how to find out the different values under this Otto cycle. Thank you very much.